I'm grateful to the Tata Institute, and in particular the Institute of Astrophysics in Bangalore, for the funding and the award of a professorship which has allowed me to be here in India. This evening I want to talk about the universe and us. I'm going to talk about our place in the universe. I'm going to give you a quick introduction to planets and stars and galaxies, although those of you who were in the Planetarium show will already know a lot about planets. I'm then going to talk about the atoms in our bodies. I will very quickly talk about the past, the present, and the future of our universe, and finally about the consequences for us. Wrong way. When I arrived here in India, I came to Mumbai airport very early in the morning, and a car drove me to Pune. We went up the Western Ghats just as the sun was rising, a great red sun, a bit like as in this painting by Joan Miro. You will have seen a red sun here at sunrise or sunset. Our sun and most of the other stars that you can see in the night sky are shining because in their center are nuclear reactions, nuclear fusion reactions. The sun, as it carries out these nuclear fusion reactions, is consuming hydrogen. 600 million tons of hydrogen every second. It's been doing that for 5 billion years and will keep on doing that for probably another 5 billion years. But not forever. One day the sun will run out of hydrogen and will stop shining. And that's true for other stars as well. They do not live forever, although by our standards they live for quite a long time. For those who like the technicalities, this is what's happening inside the sun and the other stars. There are 4 hydrogen nuclei combining, and with a bit of jiggling around, we end up with helium nucleus. The helium nucleus is a little bit lighter than the 4 hydrogens, and the mass difference comes out as energy, the starlight, the sunlight. And in the case of stars like the sun, this continues for about 10 billion years. At the end of that phase, our sun will go very red and swell. It will become what we call a red giant. It'll swell 100-fold. What's the name of the closest planet to the sun? Mercury. It will swell and engulf Mercury. It will swell and engulf the next planet. What's that? Venus. What's the planet after that? Earth. It will swell, and either it just will or just will not. We can't do the sums precisely enough. Engulf the Earth. But if the surface of the sun at a temperature of several thousand degrees comes this close, I'm not staying. The Earth will be too hot for life. The Earth will be charred, will become ash. A cinder is perhaps a better way to put it. However, after that swelling phase, or during that swelling phase, there is another nuclear reaction that a star can do. It can take 3 of these helium nuclei and combine them to make carbon. And it shines that way for a bit longer. I hope you recognize planet Earth spinning. You have to look quickly to recognize the continents, but they're all there. And here along the bottom is the solar system. I stress that it is not to scale. There is much, much more space between the planets. But if you want to get them on the one slide, you have to shunt them up close to each other. So at the left-hand end is the Sun, Mercury, Venus, Earth, and the Moon. Mars, a whole load of little things called the asteroids, Jupiter, Saturn, Uranus, and Neptune. And these are the ones that are known as the planets. Beyond Neptune there is Pluto, and we are finding many, many more things like Pluto. As our telescopes get bigger, we find more and more Pluto-like things. These planets formed from a disk around the early Sun, like a giant version of Saturn, the Sun and a ring of material around it. And these planets formed in that ring. These other dwarf planets have come from elsewhere and are not lying in the same ring. So you can think of these as birth children of the Sun, and these are grabbed later. They are adopted planets, if you like. And there are also sometimes comets. We were hoping there would be a spectacular comet around this month called Comet Ison. But as a comet, which is a ball of ice and snow and some dirt, dust, as it comes close to the Sun, the outer layers melt. The melted outer layers make the spectacular tail. But what happened to Comet Ison as it went round the back of the Sun? The snowball bit broke up into small pieces, and we, alas, did not have a spectacular tail like that. It's quite a long time since we've had a spectacular comet, and one is certainly due, but you cannot predict when they come. This is an old engraving from the Netherlands. It's dated 1709. I find it a rather charming picture, which is why I have included it. And you see lots of people out looking at this spectacular comet. Moving beyond the Sun and its planets out into the stars, one of the most prominent constellations, particularly at this time of year, is the constellation of Orion. Perhaps most easily recognized by these three bright stars in a line. Orion is the hunter, and this is Orion's belt, and here is his sword or dagger. These four stars define his body. This orangey one is one of these stars that's getting old. Like the Sun, it's gone red and swollen. It's called Betelgeuse, and Betelgeuse translates as the armpit of the mighty one. Apparently armpits were sexy. So that's one side, one armpit, down to his waist, on down the body, and there's the other. I've also put up a copy of a painting by a European artist called Kandinsky. He calls this painting The Stars. And I suspect he's thinking of Orion when he paints this. It has the same kind of overall shape. In Orion's belt there is a nebulous piece, a fuzzy part, and that's where some new stars are forming. And here Kandinsky has something which looks a little bit like a stellar womb with new stars forming. Orion is also in this picture, but it's much smaller. This is it. And I have included it And I hope on the slide you can see a very faint, broad band across the sky, just above Orion. It's called, in English, the Milky Way. It looks like a root, and it's whitish. It's actually whitish because there are many, many faint stars there. The Milky Way is our galaxy, and I'll explain shortly why it looks that way to us, because we are inside it. So I will say a bit about our galaxy, the Milky Way. A galaxy from outside looks a bit like this. And if we could get outside the Milky Way, our galaxy would look like this. It's a large number of stars, and it's spinning. This one is spinning round this way. And maybe you can see that the stars are in a kind of spiral shape. It's called a spiral galaxy. Our position in our galaxy is not at the center. It's about 2/3 of the way out in one of the spiral arms. We are not the center of our galaxy. We are not the center of anything. We have what I call a suburban address, out on the fringe of the galaxy. This painting is from Australia. It is a painting by an Australian Aboriginal painter called Rex Walford, and he calls it Milky Way Dreaming. Many of the Australian Aboriginal paintings are made up of lots of little dots, and you can perhaps see here many, many dots. And it gives the idea, the sort of whirlpool sense of a galaxy. But Rex Walford cannot have seen this, because he too lives on Earth, inside our galaxy. He will have seen the Milky Way as that band across the sky. Somebody must have shown him a photograph of a galaxy, and he's made this painting. But it's rather lovely. Our galaxy contains 100,000 million stars, and our sun is one of those 100,000 million stars. And it's a very ordinary star, an average star. It's not special in any way. Our galaxy is disc-shaped, and most galaxies are disc-shaped. And I have here, to the mystery of the director, 2 paper plates. No expense spared for this demonstration. 2 paper plates. One of them has a pattern on it. It's a spiral galaxy, like I've just shown you. We live inside this shape. It's circular as I show it to you now. If I tilt it a bit, it's elliptical. And if you see it edge on, it's really quite thin. Can you imagine living inside something of this shape? Maybe in here, between my fingers. You imagine yourself in there. If you look out upwards or downwards, you're looking through a thin part of the galaxy. You're looking past relatively few stars. But if you look out towards the rim, you're looking past a lot of stars. And so in this direction, you see a band of stars round the sky. Now, the way we see the Milky Way is often a bit tilted, but it's the same principle. Look out towards the rim of the galaxy, you're looking past lots of stars, you see lots of stars in this direction, and what you see is a band of stars across the sky. The whole galaxy is spinning all galaxies spin, all stars spin, all satellites spin, all planets spin. It seems that everything in the universe spins. And as our galaxy spins, we are moving at 200 kilometers every second. And yet we don't sense it. But we are moving that fast. The distance across the galaxy is what we call 100,000 light years. A light year is how far light travels in 1 year, and that's about 10 million kilometers. So the distance across our galaxy is 100,000 multiplied by 10 million. That makes 1 million kilometers. The numbers in astronomy are very big and perhaps too hard to imagine. I've mentioned that we're moving as the galaxy spins at about 200 kilometers per second. We're also moving because the Earth is going round the Sun. The Earth orbits the Sun. And the speed there is about 30 kilometers per second. Less than the galactic motion, but still sizable. And also the Earth itself is spinning. So, for example, if we were sitting on the equator, because the Earth is spinning on its axis, we'd also be moving at about half a kilometer every second. Significant distance in a second. So there's a lot of rotation going on, and we don't seem to be aware of any of these. Perhaps because it's always there, and it doesn't change. It's not noticeable to us. Now this is a rather dark painting. I'll show you a lighter version in a moment. It's another European painting by a German painter called Adam Elsheimer. And he painted this in 1609, a long time ago. It's said to be the first Western painting that shows the Milky Way. But what it's actually meant to be about is what in the Christian church is called the flight into Egypt. Baby Jesus, Mary and Joseph are here with a donkey, and they're moving from Bethlehem, where Jesus was born, into Egypt, because they've been told that King Herod is going to kill all baby boys. So this is what's known as the flight into Egypt. Somebody has a fire lit here, and there's a wonderful full moon. I have to say that the landscape doesn't look like Palestine. It looks like Europe. But then he was a European painter, and maybe he had never seen Palestine. Perhaps you can see a faint white line down here, broad line. That's the Milky Way. And although we won't be able to see, there are many stars dotted around here. I asked a school astronomical club to look at this painting and see if they could tell me when and where it was painted. They see the Milky Way with this sort of angle. There's a full moon. There are some constellations. And the school astronomy club had a wonderful time looking at this picture and told me that there are many constellations up here that they can recognize. But those constellations should not all be in this small patch of sky. The painter has had some artistic license, and because of this, you cannot tell exactly when or where it was painted. But it does indeed show, albeit faintly, the Milky Way. Many of us live in cities with a lot of light, and we cannot see the night sky. But our predecessors lived without street lights and floodlights and advertising and headlights and house lights. They could see the night sky much better than we could, And they were aware of the Milky Way and the constellations, and they named them. And here are some of the names given to the Milky Way. They've been translated back into English, you will understand. So the Australian Aboriginal people call the Milky Way the Rainbow Serpent. Celtic people, the Silver Street. In China, it's the Silver River. In one of the North American traditions, it's the Path of the Spirits. In ancient Hebrew, it is the River of Fire. I'm told that in Hindi, it means River Ganges in the sky. And in the Kalahari in South Africa, it's known as the backbone of the night. In Korea, it's Silver River water. In Maori, the New Zealand people, it's the long fish. In another South African tribe, the Setswana, the place where the lightning rests. This one really puzzles me. In Siberia, it was known as the Silicon River. Did they know about silicon in the old times? Or was silicon a place and the chemical element was named after the place? I don't know. I must do some Googling and find out. But it's rather an intriguing title. In Sweden, it is the Winter Road, because in winter there is a lot of dark, very little daylight in Sweden, and you can see the Milky Way very well. But my favorite one comes from Thailand. It's the Way of the White Elephant. White elephants are very special in Thailand, and so they've called the Milky Way the Way of the White Elephant. There is a video clip here that I am going to let run many, many times. It is a sequence of photographs of stars near the center of our galaxy. Each of these colored dots is a star. And you can see them moving. And up on the top left is the date. This sequence of photographs goes from about 1995 to 2011. Now, normally stars will move in straight lines. Everything moves in straight lines unless there is a force that tugs at it and makes it go in a curve. There are lots of curves here. In fact, there's only one star moving in a straight line. It is this one. And I am quite puzzled as to why it is moving in a straight line. So if any of the physicists or scientists present can explain why this one goes in a straight line when everything else is curved, I'd be interested to hear. These other stars are all moving in curves because at the position of this little star, there is nothing to be seen, but there's clearly something with a strong force of gravity. So for instance, watch this star. Curving round, whoops, and round again. This is one of the ellipses predicted by Kepler. Only Kepler was talking about planets which go round the sun. This star is going round a black hole. And as it goes round here at the bottom, it's going at about 7,000 kilometers per second. And it's pretty close to the black hole, closer than Pluto is to the sun. And indeed, every star in this diagram has its orbit curved because there is a black hole here. It's a black hole that weighs 4 million times the mass of the sun. That sounds a lot, but actually we now know that many galaxies have black holes at their center, and mostly they're more massive than ours. Our black hole is relatively tame. Our black hole is relatively tame in another sense. It's not very active. Some galaxies, they have black holes that shoot out great jets. At least at the moment, our black hole is quiet. There's evidence that maybe 1 million years ago, it was more active and shooting stuff out. But at the moment, it's certainly not. If you're interested in this, and they keep adding more data to it, more frames, as the years go by, you can find this video on the web. So I've talked about our galaxy. There are actually many, many other galaxies. And as a rough rule of thumb, I present what I call Eddington's multiplication table. Do you have the phrase multiplication tables? 2 times 2 is 4, 2 times 3 is 6. Yep, right. Here's a cosmic multiplication table due to a British astrophysicist called Eddington. He says 100,000 million stars equals 1 galaxy. He also says 100,000 million galaxies equals 1 universe. So the universe is big with an enormous number of stars. It's slightly rough and ready that galaxies aren't absolutely standard, but to give you a feel for the numbers involved, this is very good. So we live in a galaxy called the Milky Way. There are other galaxies. It turns out that the other galaxies are not uniformly spread, but they group themselves into clusters of galaxies. And we live in our galaxy in a cluster of galaxies. But astronomers are not always very creative about naming things. Our cluster of galaxies is called the local group of galaxies. It's actually not a very spectacular cluster, it's rather a poor one. And maybe group is better than cluster. And it turns out that the clusters of galaxies are not uniformly spread, but themselves cluster. And we call the clusters of clusters superclusters. And our supercluster is called the Virgo supercluster because a lot of it lies through the constellation of Virgo. We do believe that the universe had a beginning. It was about 14 billion years ago. And here I'm using billion in the American sense of 1,000 million. 14,000 million years ago, it seems that everything was in a tiny, tiny volume, smaller than a grain of sand. And it went whoosh. It expanded very, very rapidly. This rapid expansion has been given the official name of Big Bang. And you see it with capital B's for Big and Bang. It's the official title of the start of our universe. In that tiny, tiny volume, smaller than a grain of sand, was all of the universe, all of space, all of matter, all of energy. Our heads are about to start hurting. Don't worry. There's several head-hurting things on this slide, which I'll try and explain. Imagine a leaf bud about to open. Inside the bud, there is the whole of the leaf folded up. And there is also the potential for the leaf to grow. Inside that tiny, tiny volume, at the beginning of the universe, was the whole of space folded up and the potential for it to grow. And as the whole thing burst open like a leaf bud, space opened out and spread out and is still spreading out. But because all of space was folded up in this tiny volume, it means the explosion, the whoosh, took place in the whole of space. There was no one point. This explosion was everywhere. There is no center to the explosion. Here, on our galaxy, we see the other galaxies moving away from us. But if we lived on a different galaxy and looked out, we would also see all the galaxies moving away from us. There is no center. All of matter and all of energy were in this tiny volume. We now know, thanks to Einstein, that matter and energy are interchangeable. A bit like the way I convert pounds, British pounds, to rupees. And before I go home, convert rupees to pounds. You change matter into energy, energy into matter. In the very early universe, it was a lot of energy and no matter. Today, we have quite a bit of matter. All this stuff here, for example, and much less energy. The other thing I want to say about, while we're on this slide, concerns time. What the scientist calls time began with the Big Bang. From my point of view, this is great. This is heaven sent for a speaker. Because it means that if you ask me, what was there before the Big Bang? A very reasonable question. I have to say, I can't tell you. Because time began with the Big Bang, and before time began doesn't make sense from a scientific point of view. It's a bit like asking, what's north of the North Pole? It is a nonsense question. Right, let's move on. The evidence for this Big Bang is, as I've said, we see the galaxies moving apart. We can also pick up some of the original radiation. There'll be some people here who had television sets that you tuned by turning a knob. And as you were tuning between the stations, your television set went, there was a hiss. Most of that hiss, 90% of that hiss, came from the electronics inside the television set. But 10% of it is the radiation left over from the Big Bang 14 billion years ago. Now much stretched out, thinned out, and cooled. Only about 3 degrees above absolute zero, but still detectable. The third piece of evidence concerns the abundance of heavy hydrogen, deuterium, and I'm not going to talk about that in any detail. I simply want to say that the Big Bang theory looks good. It's seen off a number of competitors, and it's still with us. And the kind of research we do today is not so much whether it's true, but how some of the details work out. So initially, this Big Bang is a fireball of light and energy. But it's cooling as it expands. And this business for exchanging energy into matter begins to kick in. Einstein's equation, E equals mc squared. And some of that radiation fireball turns into solid stuff. Initially, it's not solid stuff you'd recognize, but after a few minutes, the solid stuff is nuclei, the nucleuses of hydrogen and helium atoms. The electrons are still floating loose. Atoms don't form for another 400,000 years. And stars and galaxies form about 400 million years later. So the initial universe gave us hydrogen and helium and nothing else. The universe today, I'm going to talk a little bit about stars, how stars are born, they live, and they die. This lovely photograph from the Hubble telescope shows places in these pillars where some stars form. Particularly up near the tip, there are stars forming from the dust and gas that make up these pillars. Stars take maybe 1 million, 10 million years to form. They gradually coagulate, gather material onto themselves. And as they grow, the temperature in the center increases. And when the temperature in the center reaches about 10 million degrees, the nuclear reactions that I was talking about kick in. This group of stars is called the Pleiades, or the Seven Sisters. And yes, I can count to 7, and there are not 7 bright stars there. But many, many cultures call this group of stars the Seven Sisters. So I think there used to be 7 bright stars, and some may have faded. These are extremely massive stars. They're 10 or 20 times the mass of our sun. And they're shining very, very brightly. They're the astrophysical equivalent of the young man in the sports car. They're very bright, they're very flashy, but they don't last, and there's no money in the bank. These stars will die young. They are relatively young at the moment, and they will die young because they're galloping through their resources. They're important for us and our life, as I will explain shortly. This is a group of stars that is near the South Pole. You can't see them from here. One of the stars, this star has a faint orangey color. It's one of those big stars that's swollen up and engulfed any planets it has. It's on the way out. It's showing signs of age. Our sun will ultimately end up with a coughing fit. And it'll have an extra big cough, and its outer layer will get thrown off into space. And the sun itself will become a tiny star like this, which we call a white dwarf. It's no longer got nuclear reactions, it's no longer generating energy, but it's still very hot. So it's shining because it's hot. It's like a hot coal that you take from a fire or a brazier. It shines to begin with, but as it cools, it goes from white to yellow to orange to red to brown and stops shining. This star will go from white to yellow to orange to red to brown and stop shining. And that will be the end of our sun. Big stars like the Pleiades have a more spectacular end. This left-hand slide is part of a small galaxy that you can see from the southern hemisphere. It's called the Large Magellanic Cloud. People near the front can perhaps see there's lots and lots of stars. There's a glowing mass of gas and stars here. And one of the stars is identified with an arrow. Just to be absolutely clear, the arrow was added after the photograph was taken. There are not arrows in the sky pointing to interesting stars. Look at the right-hand photograph. Glowing mass of gas, millions of stars. And this was that faint little star. It has exploded catastrophically. Wiped itself out almost totally in the process. This event is called a supernova, which is a supernova. And nova in Latin means new. Every so often, ancient astronomers saw new stars, nova, stars that brightened up. A few of them did it really spectacularly, and this is one of them. It's a supernova. I'm going to take us to chemistry for just a minute. You've perhaps seen a chart like this hanging up. School science laboratories, maybe? Something like that. It's a chart of the 100 or so chemical elements that we know about. In its top row are the two lightest elements that we've already met, hydrogen and helium. And as you go along the rows, the elements get heavier and heavier and heavier. The columns are also meaningful. All the elements in the same column have the same chemical properties. So this lot are the inert gases. They don't want to do any chemical reactions. Thank you very much. We're very nice as we are. Whereas this lot, hydrogen, lithium, sodium, and so on, are very, very reactive. And it grades across the periodic table. In Oxford, you can see the periodic table on the taxis and buses. But that's Oxford. I have some student answers to exam questions, chemistry exam questions. Some problem here? H2O is water. What's CO2? Carbon dioxide. Yep. We've met three chemical elements, hydrogen, oxygen, and carbon. And just for the fun of it, another student answer to a question, which I'll let you read. These are not Indian students, nor are they British students. They're from the United States of America, that wonderful source of all sorts of amazing things. But they have introduced us to hydrogen, oxygen, and carbon. What do you think are the most important chemical elements in our bodies? And I'll give you a clue. We're 2/3 water. Hydrogen, oxygen. What's in our bones? Calcium. Why is our bloodstream red? Iron, yes. And carbon is another major constituent of our human bodies. There are also smaller amounts of a number of other chemical elements that are very, very important, but they're not there in large amounts. The main chemical elements, hydrogen, oxygen, carbon, calcium, and iron. Hydrogen came from the Big Bang at the origin of the universe. Where have the other chemical elements come from? Here's a physicist's view of life, with apologies to any biologists, life scientists in the audience. When we were born, we were smaller, this sort of size. We're bigger now. Why are we bigger? Well, we've grown. But why have we grown? Because people do, yeah, but there's more atoms in our bodies now. Where have those atoms come from? Food and drink. Let's pretend we're all vegetarians. We eat plants, so we take on board the atoms from plants. But plants start as tiny, tiny seeds, and they grow. They take on atoms. Where have those atoms come from? From the earth? Maybe the rain, maybe the atmosphere, but all things to do with the earth. So basically, we eat and grow because we take on atoms that have come from the earth and its atmosphere. Where did those atoms come from? Well, they came along with the earth basically from the sun, left over from the sun. And you say, where did the sun's atoms come from? You can keep pushing back and back and back. But we've started with the Big Bang, and we've seen stars born and live and die. It turns out that all the carbon in our bodies, all the oxygen in our bodies, all the iron, all the calcium has come from the stars. Because it's come from stuff that made the sun, well, it was left over from making the sun. And the stuff that the sun was made from was in the galaxy, but it was stuff in the galaxy plus stuff from earlier generations of stars. It's the big stars like the Pleiades that make a huge range of chemical elements. Carbon, calcium, iron, oxygen. And when those stars explode, the material fans out through space. And some of it got gathered up into the sun. So the chemical elements in our bodies have come, with the exception of hydrogen, have come from the stars. And if it wasn't for the life and death of big stars, we would not be here. So we are intimately and ultimately children of the stars. There is stardust in your veins. We are made of star stuff. And now to something slightly less cheerful, the future of the universe. I've talked about how stars have created the heavier elements. But you don't get something for nothing. Those stars have created the useful oxygen, iron, calcium, and so on at the expense of hydrogen. They have used hydrogen up to make the calcium, the oxygen, the carbon, the iron, and so on. And there will come a time when the stars have converted so much hydrogen to calcium, carbon, oxygen, and so on, that there won't be enough hydrogen left in the universe to light new stars. Old stars will go out. Stars ultimately die. Old stars will go out. Material will gather and try to make new stars, but they will not light up because there's not enough hydrogen in them. So in the long run, million years maybe, the stars in the galaxy will go out and no new stars will light. The galaxy will go black. The black hole at the center of the galaxy and any other black holes will continue to have a field day, but nothing else moves. And that's serious news for us because we need a star like the sun to live off. We need the energy of a star. There's something else happening as well. And this is fairly recent discovery. I've talked about the way the universe is expanding. The galaxies are getting carried further and further apart. You would guess that there's still some gravity around between the galaxies, and maybe the expansion would gradually slow. No. The opposite is happening. For some reason that we still can't properly explain, the galaxies are moving apart, and they're moving apart faster and faster and faster, as we can see if you can interpret graphs. Up here is a plot of basically the size of the universe, and along here is age. The Big Bang is here, and today is about there. And the universe initially expands very fast, then expands steadily, but more recently has been expanding faster and faster and faster. The expansion is accelerating. Another version of the same thing, Big Bang, expand rapidly to begin with, expand steadily, and then go whoosh and expand very, very fast. You perhaps have heard that Einstein says things cannot go faster than the speed of light. That's true, but it's got some words missing. Things cannot go faster through space than the speed of light. But space itself can go faster than the speed of light. Einstein's theory does not apply to the stretching of space, the expansion of space. And what's going to happen here, indeed probably already has happened, and I'll go back a slide, is that we're going to see things moving away from us faster and faster and faster, and some will be going faster than the speed of light and will become invisible to us. So galaxies that we can now see out there moving away from us are going to move faster and faster and faster and become invisible. Go over a horizon, if you like, because there space is stretching faster than the speed of light. So this is a good time to be an astronomer. We can see other galaxies. But astronomers in the far distant future will see a much emptier sky as more and more of those galaxies appear to travel at speeds faster than the speed of light. The universe will become emptier, and gradually probably even our galaxy, the outer bits of it, will be stretching faster and faster and become invisible. So not only is the universe going to get blacker, the stars going out, it's also going to get blacker because of this expansion. We're still not very clear what's causing this expansion. In fact, it's probably true to say we have no clue what's causing this expansion. But, you know, as people, we always feel better if we give a name to things. It gives us a sense of power if we name things. So we have named whatever's causing this expansion of the universe, this acceleration. We've called it dark energy. Not a very creative name, but it's dark because we haven't a clue what it is. It doesn't seem to shine. And it's energy because it's pushing the universe apart. So something is causing the expansion of the universe. We call it dark energy. We can see it in about the last half or third of the universe's life, not before that. Maybe it was there but was suppressed, clouded by other effects. We're not quite sure. We're not quite sure if it's everywhere. There's a lot of research still to do. But as I've already, I think, said, as the expansion of space gets faster, things disappear over a horizon, the sky becomes emptier, and ultimately also the stars fizzle out. We live in a once and only universe, a one-shot universe. It doesn't seem to have a very, very long-term future. It does its thing, and that's it. It's not good news for humanity, because we need a sun or a sun-like star. And in the very, very long term, there won't be any such. So the really cheerful message is that we live in a universe that is cold, dark, largely empty, getting colder, darker, emptier. It doesn't have a center, doesn't have a focus. It doesn't need us. Indeed, it will actually kill us in due course. And I have to say it seems a bit amoral and purposeless and meaningless. But it's fun and it's interesting. So don't dwell too much on the future. Enjoy the present. But it's perhaps also worth noting that we are, to a degree, exceptional. This is a special part of the universe in the sense that it's, denser than average. Most of the universe is pretty thin. We're chemically atypical part in that here there's a concentration of the heavier elements like silicon and carbon and oxygen and aluminium and all these things. We're made of matter, not antimatter. The early universe contained almost equal parts of matter and antimatter, but just a fraction more matter, at the level of 1 part in a billion. We're made from that 1 part in a billion anomaly, because we're made of matter, not antimatter. And it turns out that there's a lot of stuff in the universe called dark matter, as well as dark energy, that's totally different. We, and all the stuff we study in physics, amounts to about 5% of the mass energy of the universe. And the rest is different and currently unknown. When I started in research, we thought we understood the universe pretty well. We have learnt otherwise. Instead of reckoning we understood, about 90% of the universe, we now know we understand less than 5%. There's a job to be done, folks, at the level of 95% of the universe. And I hope maybe some of the people here might take on that job. There's a very exciting future ahead for physics and astrophysics. And although I haven't a clue what it is, I know it's really, really important and exciting. Thank you for your interest. Thank you for your time.
If two galaxies or two stars come closer, will they have any gravitational force if they collide or repel anything else?
Yes, we can see quite a few galaxies merging, joining. And there's evidence that our galaxy has swallowed a number of smaller galaxies and is still absorbing, swallowing smaller galaxies. And sometimes pairs of stars will gradually merge, spiral in and merge. So yes, it does happen. When it's two galaxies, they probably both have black holes at their center. So we're talking about the merger of two very big black holes. Usually makes an even bigger black hole. But there's usually also some fireworks at the same time.
Why did you say that you thought there were not many places in the universe where creatures like human beings might have arisen?
Unless we can find a way of getting energy from a black hole and live near a black hole, which is a bit risky, we actually have to have a star like the sun and live near it, because we need the energy from the sun to make the plants grow, to keep us warm, to keep us fed. So we actually are very dependent on the energy from the sun. When the sun expires, we could climb into spaceships, go find another star that has a planet like the Earth, preferably uninhabited, and go colonize that planet and live off that star.
Do you think there's intelligent life likely elsewhere in the universe now or not?
Right. One of the very surprising things that we found in the last 10 years is that a lot of the other stars have planets, far more than we ever imagined. If you look at the night sky, imagine you're somewhere dark, you can see about 6,000 stars. There are also about 6,000 planets up there. There are as many planets as there are stars. So lots and lots of planets. Our techniques won't yet allow us to discover many Earth-like planets. That is, planets at the right distance from the star so that water is neither evaporated into steam nor frozen into ice, where there is liquid water. But I'm sure those planets exist, and I'm sure we'll find them. And amongst people who work in this exoplanet field, the judgment is that within about 100 years, within the next 100 years, we will have evidence of life on another planet, probably around another star. Whether it's intelligent life is another question. It might be simple cellular life. But personally, I think this is coming sufficiently close that humanity needs to start thinking about how we approach other civilizations on other planets out in the galaxy. Are we going to assume they're friendly? Are we going to assume they're dangerous? Are we going to collect some specimens and put them in a zoo? Are we going to eat them? Will the Americans want to send in the GIs to bring them democracy? How are we going to approach this? And I think we need to start thinking about that, because 100 years is not very long for this kind of big change that's coming.
The physics, whatever we know today, is enough to explain all this, or like we want to, like from mechanics to we have this special relativity, then we have general relativity. That kind of physics has to evolve to explain all this.
That's a good question, and it's not completely clear what the answer is. I think one of the biggest challenges is something I've not talked about a lot, called dark matter. It turns out that dark matter can't be made of this sort of stuff, or the stuff that we're made of. It cannot be made of neutrons and protons. It has to be something totally different. And we're still not clear what that is. Maybe it's made of some of these rather exotic supersymmetric particles. Time will tell. But I think that is going to make a big change in physics. And if that doesn't, then understanding what dark energy is will certainly make a big change in physics. I think there's another revolution in physics coming very soon, as we endeavour to understand what these things are.
Is there only one universe or millions of universes like this?
A good question. Are there millions of universes? Well, actually, because we are inside our universe, we can't really answer that question. But it doesn't stop people wondering. And there are some very creative ideas around, which we may never be able to prove right or wrong. But one of the most common pictures is that there are lots and lots of universes. Imagine you have been washing dishes and there is some soap, foam left in the sink. Lots and lots of little bubbles. Maybe our universe is one little bubble and there are lots of other little bubbles all around us. And some of the bubbles are expanding and some of them are bursting, and each is doing its own thing. That's a picture that's quite popular. I don't know how we establish whether it's right or wrong, to be honest. But of course people are imagining what there might be.
In the center of each galaxy there's a black hole. Doesn't that, and we have stars revolving around each black hole. Does that mean that the black hole itself has an axis? And how would you explain other shapes of galaxies with the black hole at the center?
Yes. Black holes, we suspect, do have an axis, because when black holes are being active, they tend to spit out a couple of jets, very fine jets. And this is probably along the spin axis of the black hole. At least that's the assumption at the moment. We may get proved wrong, but we do imagine that there is such a spin of the black hole. I've talked about spiral galaxies. Some galaxies are what we call elliptical. Do you have rugby in India? Play rugby? Like the shape of a rugby ball, but they also spin.
More hydrogen be formed?
Could more hydrogen be formed? Only if somebody finds some way of splitting the atoms that have been made inside, splitting the nuclei that have been made inside the stars. And as we understand the processes at the moment, the answer is no. The only thing that could happen is that maybe helium, which is normally the second stage of burning, maybe helium could become the first stage. But it's not a very long stage, so even if it could be made to happen, I'm not sure it's terribly useful. So I'm sorry, I don't have good news for you. We don't know enough about dark energy to know whether it was there in the early universe. If it was there, it wasn't showing. But then there was a lot of other stuff going on in the early universe, and it might just have been that the other stuff dominated and, so to speak, hid the dark energy. The dark energy only began to reveal itself about a half or a third of the way, half or 2/3 of the way through the life of the universe.
Solar system, Pluto is one of the planet. About 15 years back, we concluded. But now that planet is not considered, that is not a member of the solar system. What is the specific reason is there for?
It is still a member, Pluto is still a member of the solar system, but it's no longer one of the classical planets. Two reasons for this, and I was quite closely involved in this decision. Pluto has a very different orbit from Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune.
So,
If they go round like this, round the sun, Pluto is doing this. It's totally different. And it's because it was not formed at the same time as the other planets. It has a different history and was acquired by the sun later. And now with big telescopes we're finding other things like Pluto. And here's the Mercury out to Neptune. All these other planets do things like this, or this, or this. They're totally different orbits. They are much, much smaller. Pluto is smaller than many of the moons round the classical planets. It's different in many, many ways. It has a moon which is very, very big. And so you can sometimes think of Pluto and its moon Charon as a pair of planets. Charon, the moon, is so big. It's just anomalous in so many ways. And another reason is we teach school children about the planets, but we're finding more and more Pluto-like things. So this year we would teach them Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, Quar, Mahi-Mahi, Sedna, Eris, and next year the list will be longer. It'll have grown, and the year after it will grow. That's crazy. We can't be teaching our children something different every year. It's better to make the distinction between the 8 planets that we know about and this growing number of dwarf planets.
We know what matter is, but what is antimatter, and have scientists been able to prove the existence of antimatter? Has it been scientifically proven or something?
Yes. Antimatter sounds dramatic, but it's actually not that peculiar. And scientists have been aware of it since Dirac, getting on for 100 years. It's very like matter, like ordinary matter seen in a mirror is perhaps the best way to explain it. It's got, some of its properties are opposite. You know, when you look in a mirror and you touch your right ear, the mirror says you're touching your left ear. It's a bit like that with antimatter. But it's not so peculiar, to be honest. And we see it regularly in things like the big particle accelerators. We can see it in some parts of space. It's around a lot.
What is the extent of space? What is the concept of space? How far it is? How big it is?
Right. That question, how extensive is space, is actually now getting impossible to answer, because we already think some of space has become invisible because it's going faster than the speed of light. And with time, more and more of space will become invisible. So if you could tell me how much there was that's going faster than the speed of light, we might be able to answer the question. But we can't know how much is going faster than the speed of light. So I'm afraid it's another question where the answer is we don't know.
I've read that immediately after the Big Bang there was a thing called inflation,
Yes.
and how all the fundamental forces froze out technically. So can you explain how exactly that happened?
This is the expansion of the universe. Starts with the Big Bang, expands very fast to begin with, and then expands more slowly. This very fast expansion is what's called inflation. And it happened in the very early universe. And the universe expanded actually faster, apparently faster than the speed of light. But because it was the whole of space expanding, that's all right. Well, as you alluded, it is something to do with the fundamental forces and the way the universe was coming into existence.
These concepts of dark energy and dark matter, so are they same or different? What is
I suspect they are not the same, because dark matter acts in the opposite way to dark energy. I've talked about dark energy making the universe expand faster and faster. Dark matter is actually something that provides more gravity and holds things together. For instance, I showed you a picture of a spiral galaxy and said it was rotating, spinning. It's actually rotating so fast that you would expect it to fly apart. There does not seem to be enough gravity to hold it together. So astronomers have had to invent dark matter to provide extra gravity by something that does not shine. So it's dark, but it's matter because it's got gravity. So dark matter and dark energy act in opposite ways. The only thing they share is they're both puzzles with very little clue what they are at the moment.